How about the general case? What if we have, as we normally do, a matrix which is a little bit more complex than an elementary matrix? So a matrix which is obtained maybe from the identity, maybe not from the identity, we don't know, but it's just some complicated thing that comes from nowhere. Again, square matrix. Okay? Well, it turns out that if a matrix can be row reduced to the identity matrix, so if I start from my matrix, so I compute the RREF, and I get the identity matrix, okay, then it is invertible. Okay. Now, this again is a very nice thing. So it gives us a very strong condition and very simple condition for knowing if a matrix is actually invertible or not. But this is not the end of the story. In fact, what I'm going to show you is not only that this is true, but I'm going to show it by giving you a method for finding the inverse. Okay. Now, first of all, let me show you why this is true. So let's start from a matrix A, okay, and let's say that I can row reduce it to the identity. What does that mean? It means that I can start by picking one row operation, that means multiply by an elementary matrix, another one, a few more, and then a whole bunch of them. And when I do all that sequence of row operations, each of which is equivalent to a product by an elementary matrix, I end up with the identity. That's what I'm saying. So if a matrix can be reduced to the identity matrix, then I should be able to write that equation down for some suitable elementary matrices. But hey, look at that left-hand side. What do we have? A bunch of matrices whose product times A gives us the identity. Well, that's exactly what we need for our inverse, right? So the product of all those elementary matrices is the inverse we're looking for. And so this shows that in fact this is true, that any matrix that can be row reduced to the identity is invertible. But if you think about it, and if you stop and consider it for a minute, this same proof gives us a way of constructing it. Because in order to compute an inverse, all I had to do is the following. I'm going to start from a matrix A. Then what I'm going to do is I'm going to construct a slightly bigger matrix, in fact twice as big, by augmenting it with the identity matrix. So far we have considered augmented matrices only when we were adding the one column of constants. But this time we're going to augment it with the whole identity matrix. Then what we're going to do is we're going to take this big matrix and apply to it enough elementary row operations so that A becomes the identity. Okay? So let's take that big matrix, apply both to the left and to the right hand side all these matrices, and let's see what happens. Well, we end up with a huge, well, not really that much bigger, but a big matrix that looks like this. Now, first of all, on the right hand side, notice that we have the product of all those elementary matrices times the identity. But of course, multiplying by the identity doesn't really do anything, so we can simply make that identity disappear. And so what are we left with? Well, on the left side of that matrix, what do we have? We have En times En3, 2, and E1 all the way up to A. And if you look up just a couple of inches above, what you'll notice that that is exactly equal to the identity matrix. Okay? And on the other hand, if we look at the right side of that matrix, what do we have? Again, look a couple of inches to above and to the right, you'll notice that that product is equal to A inverse. So once we do this process, by the time we've reached the identity on the left hand side, we will be left with the inverse of the matrix on the right hand side. Now this proof to me, the first time I saw it, looked too simple and too short to be true, but in fact you can follow through it and there is not a wrinkle of an argument of a wrong argument in there. So you want to review it again and convince yourself that it is true. Okay. Now, what happens if the RREF of A is not equal to the identity? Well, in that case, it follows that A does not have an inverse, in which case we call it a singular matrix or a non-invertible matrix. Okay? Here is another tall claim, but this one I'm going to leave it to you. See if you can prove it on your own, and probably you're going to see it in class. Okay? Instead, what we're going to do is we're going to have an example. Simple example just to get the ideas clear in your mind about what we're going to do. So we're starting from this matrix. Notice at this point I don't even know if that matrix is invertible or not. I have not done its RREF, so I don't know if it reduces to the identity or not. But with great faith, what I'm going to do is I'm going to try and apply the process. So what I'm going to do is, first of all, I'm going to augment that matrix with the identity of dimension 2, of course. So I have this bigger matrix. And then I'm going to do a whole bunch of row operations, the usual ones. Switch to the two rows. But notice I'm switching the two rows throughout. Okay, so it's not only the left hand side that I'm switching the two rows, but the right hand side as well. Then I'm going to do row 2 minus 2 row 1, but once again I'm going to do it throughout, not just at the left side. Okay, so whatever I do on the left hand side, I do to the right hand side of that augmentation bar. At this point, just to keep things from generating fractions, I'm going to multiply the first row by 7 and the second row by 5. So I end up with these numbers. Again, I keep track of those operations, both left and right. And finally, I do row 1 plus row 2 to get my remaining 0. And finally, I divide everything, I divide the top by 7 and the bottom by negative 35, and I end up with this. So on the left hand side, now I've got my identity matrix 1 0 0 1. What do I have on the right hand side? My inverse. And I'm just noticing now that my A somehow lost its boldness. I'm not sure why. But anyway, it's still the inverse of the matrix A. And in fact, you might want to check that this is true. So take the matrix A, multiply it on the left of A, see that you get the identity, and then multiply it on the right of A, see that you get the identity. And so again, this is just a little illustration of how this technique works. We're going to do more examples in class.